Just a little pump you up music to get you going through this parametric equation business. All right, so we are taking parametric equations now, and we're going to use them to show motion in a plane or motion of an object. Okay, so it can be shown, and by the way, these notes are on a note sheet. I'm not as smart as Mrs. Hill, so they're in a different spot and they're in a different little part of the page because Mrs. Hill hasn't taught me yet how to embed them right in with the video. So it can be shown that if we use calculus, that if an object is thrown or launched straight up, vertically into the air. So if I took this Cheerio and I threw it up, it would go straight up and then it would come straight back down if there were no wind, no other factors. And if I threw it perfectly straight up, come straight back down, and it would land in this right below the spot where I threw it in. Okay, I'm going to eat my Cheerio. Okay, so if we launch it into an air from an initial height of h sub 0 feet above the ground with an initial velocity of v sub 0 feet per second, then the height of the object t seconds after it is thrown can be modeled by the function. There we go. There it is. H of t equals negative 16 t squared plus v sub 0 t plus h sub 0. And so we've got the three different factors that are affecting that Cheerio on it. This first one, negative 16 t squared, that's gravity. You've probably seen that in some science classes, or if you're in physics, you've probably seen that. That's the gravity constant. So as soon as that object leaves the launching, gravity immediately starts taking hold of it. That's where that negative 16 t squared comes in. V sub 0 t, that's going to represent how fast we go. If I throw this Cheerio up with very little effort, it's not going to go very high. If I really crank on it and throw it way up high, it's going to go much higher. The top of, or the maximum height is going to be a lot more. And then h sub 0, that represents our starting distance off the ground. Okay? So with that all being said, so if I have from the top of a 30-foot building, a ball is thrown vertically upwards with an initial velocity of 50 feet per second, what does the ball do? Okay, well, there's our, so here now we called it S of t. Why, I don't know. I didn't have a chance to go back and edit all these notes and all that fun stuff. Okay, so that function that we're going to have then is we're going to have, and now when we graph it, or when we put it into a graphing calculator or something like that, we're going to change our t's to x's so that they can all be graphed. Okay, the depiction, let me see if I can get, there it is. So the depiction is going to look like this. Okay? So here's our 30-foot building. We take it, we're at the edge, we throw the ball straight up. The ball is going to go up, 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 up. It's going to end up stopping. Then it's going to come straight back down and hopefully miss us standing right here on the edge of the building and come straight back down, and then it's going to hit the ground. Okay? So when I graph this s of x function on a graphing calculator, so now it would be negative 16x squared plus 50x plus 30 being, so this is our initial velocity, this is our initial height. When I go on there, it looks like, whoa, what's going on with that? Well, let me zoom out a little bit on this. Oops, grab the wrong one. There's the axes. Okay. So it goes up and up and up, and then let me see if I can, oh, I'm just gonna do this a different way. We'll graph it we'll do it in our window. Okay, so our x's, we don't have to go very far. Let's go from negative 1 to 6. And our y's, we can go from, let's go from -10 to, I don't know, let's guess here, let's say 200 feet. Okay. So there it is. Okay. So it actually looks parabolic when I graph the function, but the actual motion of that ball is just straight up and down because this is a function. Let me get back to it here. Actually, I got it right here. This is a function where x is representing time. Okay, so this is not, x here is not horizontal distance in this particular case because it's just the ball is going straight up and coming straight back down. X here now represents time. And so this is the ball, this is where we launch it. The ball goes up to a maximum height of 69.1. We can find that by finding the maximum of our parabola, analyzing the graph, etc. And then it comes back down and it will land on the ground 3.64 seconds later. So we launch it, 3.64 seconds later it hits the ground 30 feet below where we launched it. Okay? Now, so that's the function mode of that. We can also make this be in parametric mode, which will show us the actual flight of the ball. And so what we can do is we change our grapher over to parametric mode. So let me get back into my grapher here, and now let me get a new page here. I'm going to have a graph, and so on here I'm going to change this into graph entry edit there. Now I'm going to go to parametric mode, and by parametric mode, now what that does is that gives me an x function that I have to graph, and in this case, because there is no horizontal movement of that ball, that could be anything. So on the picture that I have, I have it at 5, but that number could realistically be anything. If I wanted it to be 72, it could be 72. If I wanted it to be -8, it could be -8. That number means nothing other than the fact that it is going to set where this line is. So this line is just going to be 5 over, and the reason I chose 5 over, to be honest with you, because then the function fit in here nice and perfectly and you could see it. That's really the only reason why I chose that. Okay. Then, if for my y's, now this is going to be the height function. So this is going to be -16, but now it's going to be t because my function is of t. -16t squared plus 50t plus 30. Okay? And we saw on the other one that it's going to land at 3.64 seconds. If we didn't change that at all, it would still work. The only difference would be that our function would continue below the supposed ground level. Okay? And then our t-step is just how often that it's going to be calculating it. Oops. Tab. So 5 again, -16t squared plus 50t plus 30, and then 3.64. Forgot to hit enter. There it is. Okay. T9. Whoops, I don't know what was going on there. Okay, so then we can change our window. Now we know, based off of our window settings, that we need to be out at 5 because that's where that is. So let's go with -1 to 7. Go by ones. My maximum, let's go -5. My maximum height was 69.1. So we'll go up to 70. We'll go by tens. And there's that function. And then now I can bring this over here, and there it is. Now, it didn't go all the way down here, So what I can do is I can adjust this to be a little bit bigger number. Let's just say 4. Oops. Remember I got to hit enter. Okay. And then so there again, now it went all the way down. The closer you have to get there, so like I could have gone 3.7. And there, see now it's a little bit below the line is where it stops, but it's closer to it. It's stopping like that. Okay. All right. So that is that. Parametrically, we can show that, and then I can also show you too, while we're in here, that if I change this number to 3, the only thing that changes is it just moves it over to 3. It's just that's all that X value does when you're dealing with just one vertical motion. Now, sorry, we had a pause there. Now, the kicker is that what if we throw an object or launch an object not vertically? What if we launch it at an angle? Well, we can handle that, and we can do all of this launching at an angle stuff because we did vectors in the last section. Okay? So now the topic is, what if we are standing at the top of our 30-foot building again, and a ball is thrown at an angle of 65 degrees with an initial velocity of 50 feet per second? Well, what's going to happen is our parametric equation is definitely going to be affected. Let me see if I can get this all in there without giving it away. So now we're going to, here would be our 30-foot building. Again, let me draw that 30-foot building in there. Okay, so this is the 30 feet right there. Okay, and now we're going to launch it at an angle. The ball's going to continue to go up. Then gravity is taking a hold as it's flying out, and then gravity is going to pull it back down, and it's going to end up somewhere over there. So what we need to do is we need to set our initial velocity, and we can set our initial velocity with this vector v sub 0 times the cosine of theta, v sub 0 sine of theta. And that's going to be the initial velocity, the initial launch of the ball. Now let me see if I can get this back here. Okay, so that's going to be the initial launch of the ball right in here. So that's going to be how we launch it that way. Boom, there's our initial launch vector. Parametrically wise now, what we can do with that maybe is, there we go, well maybe, there we go. Parametrically what we can do with that is, now we can take our x part, so that's going to be our horizontal distance of our object, v sub 0 cosine of theta times t. That's going to set our our horizontal distance from our launching point. Y sub t is going to be the vertical component then of that, and then again, now because we're launching an object, gravity is going to take effect, so negative 16t squared plus v sub 0 sine of t, or sine of theta times t. That's the vertical component from our vector, gravity still taking a hold, and our initial height that we launched it at. Okay? Now, let's see all of this poetry in motion.
Untimed play. Packers are trailing 23-21. Obviously, this is an all or nothing. Aaron Rodgers alone in the shotgun. 3 receivers left, 2 to the right. Snap to Rodgers. Scrambles to his left, under pressure, rolling right, escapes. Right side
he throws
looking.
it here, and he throws a perfect rainbow, as Wayne Larrabee says.
And it is caught. Touchdown. A leaping touchdown catch is made, and the Packers have won.
So here's another view of it. Okay, so he scrambled out to the right, and then he launched this parabolic arc all the way up, almost hit the girders there, and comes right back down, and there it is.
Makes the touchdown.
Okay. So that is what we're talking about here. So that would be the arc of Aaron Rodgers' throw. Okay, and we can find maximum height, we can find distance, we can find all those different things. Okay, all right. So this is a formula that I'm going to make sure that you guys have written down again. Okay, so a ball or an object launched at initial angle of theta degrees with an initial velocity of v sub 0, initial height of h sub 0, has a position. So we can find the position of that object at any time t utilizing this. The x is going to give us the horizontal distance we are from the launch. The y is going to give us the vertical distance above the ground. Because we have this, it's going to be the vertical distance above the ground of that at any point in time. Okay? Love it. Love it, love it, love it. All right, so let's put this all into work. I'm going to pause the video here. Make sure that you, or I'm not going to pause the video. You should pause the video. Make sure you've got that written down correctly because we're going to utilize that a lot in the next coming days. I couldn't handle the quarantine beard anymore, so I shaved it off yesterday. Here we go. Let's do this. Okay? Big Al hits a ball at an angle of 28 degrees with an initial velocity of 75 feet per second at a height of 3.5 feet. Will he hit a home run if the ball follows the left field line where the Little League fence is 190 feet away and 4 feet high? Now, for those of you that don't know who Big Al is, let me introduce you to Big Al.
Hi, my name's Alfred D'Elia. At home they call me Big Al, and I hit dingers.
Big Al hits dingers. Okay? All right? So we're trying to figure out if Big Al hit a dinger. Okay? So we've got two different parametric equations going on here. So the first parametric equation is going to be the ball equation. So the ball is hit at an angle of 28 degrees with an initial velocity of 75 feet per second at an initial height of 3.5 feet. So what we're going to do here is we're going to make a ball function. Oops, I guess I can't do this without giving away this one. Okay? So here is the ball's position. 75 is my initial velocity. 28 degrees is my initial angle. So that's why we got 75 cosine of 28 degrees times t. Negative 16 t squared plus 75 sine of 28 degrees t plus 3.5 would be the vertical component. And I just chose 3 seconds for the ball being in the air. We'll be able to see that when we get to our function. When we graph this function, let's graph this function right here. Okay, so I'm changing to parametric mode. So my first one was 75 cosine of 28 degrees times t is my horizontal one, negative 16t squared plus 75 sine of 28 degrees times t plus 3.5 is my other one. And I'm going to actually put it short. I'm going to say, let's only go for 1 second. Okay, so shabam, there it is. Can't really see it. Let's adjust our window settings. So now X, that's going to be horizontally. We need to see if that ball can go 190 feet. So let's see if we can get that ball to go 190 feet, which means I need to go out to at least 190 feet. So we'll go out to 200. Okay, then my Y's, now that ball's going to go up and it's going to get off of the ground for a little bit. So let's go from -10 to, I would say, let's see if it goes 30 feet in the air. We'll know instantly when we see the graph. Oh, okay, so there it is. We're good there. But so that's the flight of the ball in 1 second. Okay, so that's why we chose 3 seconds, because now the ball, yes, it does go on, it does go below. Okay, we could calculate that zero-ness right there if we wanted to. We could calculate that by setting this y function equal to 0, and that's going to give us the time that it takes to get out there. Then we put that time value into this function, and then that would be how far out the ball would land. Okay? That's one way of doing it. Now, another way of doing it is, because we're dealing with a function here, we can also do the walls function. So the wall is 190 feet away and it's 4 feet high. So how we can do that parametrically, how I can quote unquote build the wall parametrically, is I can go, this way. I want to set it at 190 feet because that's how far away the wall is. And I'm going to set this at, t. And I'm going to make this go from 0 to 4. So it's going to calculate the height of the wall from 0 feet to 4 feet at 190 feet away. And there's my wall right there. Okay. So Big Al did not hit a dinger on this particular home run, or on this particular swing, I should say. Okay. He actually came up short. So let's go back into this, and there we go. Big Al did not hit a home run. Okay. Now, the question next is, how much harder will Big Al need to hit the ball to get the ball over the fence? Well, if we have a graphing type thing, most of you are probably using Desmos. Some of you have your Inspires. What we can do is we can go into our function here, and we can change this 75. Let's make it 80. And what that's going to do is that's going to change the velocity, the initial velocity of our ball. So now we made it 80. Okay, got a little closer. Still didn't make a home run though. Let's go 85. And we got to change them both. He hit it high off the wall, but he did not clear the fence. Okay, so then let's go 86. We're getting closer, so we can go by ones here now. Oops. Enter, Linsmeyer. Come on. Better than this. And that one, now if I were to zoom in right on there, that one clears the fence, and it just barely clears it. So that's why we chose 86 as the velocity, the initial velocity that Big Al, who likes to hit dingers, okay, would have to hit that ball at that launch angle. Now, if we change the launch angle, then we would change the initial velocity. Okay? Any questions? We're here all week in office hours from 10:30 in the morning to 11:30 in the morning, 2 to 3 in the afternoon, or shoot us an email with a question and we'll get back to you as soon as we can. Okay? Have a great day. Stay safe.